Now let's see the next result. Z1 times Z2 bar plus Z1 bar times Z2 is 2 times mod Z1 into mod Z2 times cos of the difference of the arguments. Now, if you observe, Z1, Z2 bar complex numbers whole conjugate is same as Z1 bar into Z2, right? This is an important observation from us which we learned at the time of conjugate of a complex number. Then, what would be the sum of Z1, Z2 bar plus Z1 bar Z2? Yes, it would be these two are two conjugates of each other. Then the sum of conjugates of two complex numbers would be 2 times the real part of Z1 times Z2 bar, isn't it? Now, how will be the product Z1 into Z2 bar? When Z1 is taken as R1 times cos theta 1 plus I sin theta 1, and when we take Z2 as R2 times cos theta 2 plus I sin theta 2. Now we have a Z2 bar in the product. Then what does Z2 bar, the conjugates property says? Magnitude remains the same. The amplitude differs by a sign. So this becomes cos minus theta 2 plus I sin minus theta 2. Only the argument changes the sign, but the magnitude remains the same. Now we have Z1 and Z2 bar. So can you tell me how much is Z1 times Z2 bar by the property of multiplication of complex numbers? It would be the product of the magnitudes times cos of sum of the arguments. That means theta 1 plus minus theta 2. Can we write it as theta 1 minus theta 2 plus I sin theta 1 minus theta 2? Right, you are multiplying with the conjugate. That's why there is a minus sign here. Now, this is your complex number Z1 into Z2 bar. Then how much is the real part of this complex number? That would be 2 times R1 into R2 times cos of theta 1 minus theta 2, where R1 is the magnitude of the first complex number, R2 is the magnitude of the second complex number times cos of theta 1 minus theta 2. So what is sum of Z1 into Z2 bar plus Z1 bar into Z2? It was 2 times modulus of Z1 into modulus of Z2 times cos of the difference of the arguments of the two complex numbers. Right? Let's proceed to the next important observation. If Z1 and Z2 are complex numbers such that mod of Z1 plus Z2 equal to mod of Z1 plus mod of Z2, then Z1 by Z2 is a purely real number. Now what does the result says? Given that mod of Z1 plus Z2 is same as mod Z1 plus mod Z2. Now, what happens if we square this result on both sides? We get mod of Z1 plus Z2 the square should be equal to mod Z1 plus mod Z2 whole square. Now the right hand side is purely a real number square, so which is in the form a plus b whole square, and for the left hand side we just derived the result. So what happens when we substitute mod of Z1 plus Z2 whole square, that is mod Z1 square plus mod Z2 square plus 2 times mod Z1 into mod Z2 into cos of the difference of arguments should be equal to, how will be the expansion on the right hand side? It would be mod Z1 square plus mod Z2 square plus 2 times mod Z1 into mod Z2, right? Now, Z1 square, Z2 square factors can be cancelled on both the sides. 2 and mod Z1, mod Z2 can be cancelled on both the sides. Then what are we left out with? We got cos of theta 1 minus theta 2 should be equal to 1. Now, when do we have cos of an angle is 1? This is only possible if it is cos 0. So can we conclude theta 1 minus theta 2 should be 0 degrees? But what is theta 1 minus theta 2? This is the difference of the arguments, that is argument of Z1 minus argument of Z2 is 0 degrees. But what is argument of Z1 minus argument of Z2? That is argument of Z1 by Z2. The difference of arguments of two complex numbers will be the argument of the ratio of the two complex numbers. Now look at this condition what we got. Argument of Z1 by Z2 equal to 0. Then what can you say about the complex number Z1 by Z2? It's a complex number having 0 argument. Therefore, Z1 by Z2 should be along the real axis of the Gaussian plane. When a point is on the real axis of a Gaussian plane, shall we say this is purely real, right? So this is a very important condition for the ratio of two complex numbers to be purely real. When will be the ratio of two complex numbers be purely real? Provided their modulus of their sum is equal to sum of their individual modulus, then Z1 by Z2 will be always a purely real number. Now let's look at the next property. If Z1 and Z2 are two complex numbers such that mod of Z1 plus Z2 equal to mod of Z1 minus Z2, that is, the modulus of the sum of the complex numbers is same as the modulus of difference of the complex numbers, then Z1 by Z2 is a purely imaginary complex number. Now for this also, let's consider mod of Z1 plus Z2 given condition is equal to mod of Z1 minus Z2, right? What happens when we square it on both sides? We know the expansion of mod of Z1 plus Z2 whole square, that is mod Z1 square plus mod Z2 square plus 2 times mod Z1 into mod Z2 times cos of theta 1 minus theta 2. This should be now equal to, what is mod of Z1 minus Z2 whole square? Mod Z1 square plus mod Z2 square minus 2 times mod Z1 into mod Z2 times cos of theta 1 minus theta 2. Now when we cancel Z1 square Z2 square values and 2 times mod Z1 Z2 and 2 times mod Z1 Z2, what do we end up with getting? 2 times cos of theta 1 minus theta 2 becomes 0, right? As 2 cannot be 0, this would be same as cos of theta 1 minus theta 2 is 0. But 0 is same as writing cos of plus or minus pi by 2. Now look at this. Theta 1 minus theta 2 is now same as plus or minus pi by 2. But what is theta 1 minus theta 2? Theta 1 is the argument of Z1 minus theta 2 is the argument of Z2. But what is argument of Z1 minus argument of Z2? It is the argument of the ratio of the complex numbers Z1 by Z2. Now, argument of Z1 by Z2 is plus or minus pi by 2. What do we mean by that? Z1 by Z2 is a complex number which is having an argument equal to 90. Then the complex number Z1 by Z2 should be along the imaginary axis in the Gaussian plane, right? When a complex number is in the imaginary axis of a Gaussian plane, then shall we say Z1 by Z2 is a purely imaginary number, right? That's what this result says. Let's see one more important observation on the similar lines. Mod of Z1 plus Z2 whole square equal to mod Z1 square plus mod Z2 square. Then also Z1 by Z2 is purely imaginary. Now given condition says mod of Z1 plus Z2 the square should be equal to mod Z1 square plus mod Z2 square, right? But we have an expansion for mod of Z1 plus Z2 whole square. What does it say? It is mod Z1 square plus mod Z2 square plus 2 times mod of Z1 into mod of Z2 times the cos of the difference of the arguments. This should be equal to mod Z1 square plus mod Z2 square. Let's remove the common factors on both the sides. Then as mod Z1 and mod Z2 cannot be zeros, the only possibility is cos of theta 1 minus theta 2 should be 0. But when will be cos of an angle becomes 0 with the amplitude lying between minus pi by 2 to plus pi by 2? This should be equal to cos of plus or minus pi by 2. So what is the conclusion we have? The difference of the arguments theta 1 minus theta 2 should be equal to plus or minus a right angle. But theta 1 is the argument of the first complex number and theta 2 is the argument of second complex number. And again argument of Z1 minus argument of Z2 is the difference of arguments is same as the argument of ratio of the two complex numbers, right? So argument of Z1 by Z2 is plus or minus pi by 2. What do we mean by that? Therefore, Z1 by Z2 is a complex number whose argument is either plus 90 or minus 90. Can you look at the complex number Z1 by Z2 now? Yes, it's a point on the imaginary axis in Gaussian plane. When a point is on the imaginary axis of the Gaussian plane, then this complex number Z1 by Z2 is a purely imaginary complex number, right? So we have seen certain conditions using polar form of a complex number to identify whether the complex number is purely imaginary or purely real, right? Let's not by heart these conditions, but we can use the procedures to evaluate the imaginary characterization or real characterization of a complex number. Let's proceed to use these results and the different representations of complex numbers to solve the following problems.